Hello and welcome back to your Chem 4 lecture. Today we're going to wrap up chapter 10 by talking about the pH scale and finish up a few minor points here for acids and bases. The main thing from today is going to be the calculation of pH. That's going to be on the test, the next test. Some of the other stuff we won't include on the test, but we'll talk about that as we go through it. So let's go ahead and get started. So this right here is a pH meter. What it is it's actually an electrode with a very sensitive skin for detecting the presence of protons or hydronium ions in solution. And based on that concentration, you can determine whether a substance is acidic or basic, like we covered in the last lecture, or you can calculate the pH. And the pH is just our measure of acidity and basicity. So, as I mentioned, the pH is used to indicate the acidity of a solution, and the range is usually from 0 to 14. When values are less than 7, the solution is acidic. When the value is exactly 7, that is exactly pH equals 7, then the solution is neutral. And then when it is above 7, it is basic. So keep in mind, again, this might be like an inverse scale from the way you might think of it normally. But again, just acidic solutions are low pH, basic solutions are high pH, is the way you can think of it. And there's a couple of different ways that you can measure it. So the pH meter that we showed at the beginning, the slide at the beginning, that's an example of a way that you can measure pH. If you need a more mobile solution, there is what's called pH paper. pH paper uses indicators like phenolphthalein, for example, to turn a color, and that specific color will tell you the specific pH value. So you can kind of decode it. So you would find the pH of the solution by comparing the color of the paper that you stick in the solution to a chart. So yeah, Pheidrion is kind of the classic one here, where basically it's a mixture of different indicators that each change color depending on the pH of the solution. And it ranges from, a dark red, which is very acidic, to orange, to yellow, yellow-green, which is neutral, and then green, starting to get basic, and then blue, and then very dark blue at the very basic end. So a very convenient way to be able to measure pH. And then, of course, you can use individual indicators like what we've seen with phenolphthalein that can switch its color in different pH values. So, sorry, I know this chart is really hard to read here, but just to give you an idea of what the pH values are for some common substances, neutral water is, water that's pure, so not from the tap, is 7.0 pH, so exactly neutral. So this would be, for example, distilled water or water that's been purified by reverse osmosis, for example. Drinking water comes from the tap, tends to be slightly basic, so it's at about 7.2. Milk has an acidity and a pH at about 6.4 compared to urine, which is at 6.0. Bread at 5.5. Coffee, if you're a coffee drinker, you may have like a heartburn from drinking black coffee, and that's because its pH is 5.0, so acidic. Of course, the juices, think like orange juice, apple juice, tomato juice, are all very acidic. They contain a lot of carboxylic acid-based acids. And then we get into carbonated beverages, which contain carbonic acid, and usually at about a pH of 3.0. Lemon juice has a pH of 2.2, so extremely acidic and very sour, right? As you drink lemon juice, you would know. Gastric juice, that's your stomach fluids, has a pH of about 1.6. And that's about the most acidic thing inside your body. So as far as fluids go anyway. Now, if we're talking about in laboratory, the pH of a 1 molar hydrochloric acid solution is exactly 0.0. So that's an example of like the very low end of the pH scale. Now, as we go down to the basic stuff, we mentioned drinking water already. Blood plasma as well is basic because it contains a lot of hydrogen carbonate, We're going to talk about that when we talk about buffer systems at the end of the chapter. Bile fluid is 8.1, and that matches up laundry detergents pretty well. Seawater as well has a basicity, or is basic, and has a pH of about 8.5. Milk of magnesia, which is kind of a common antacid, I guess you would say, has a basicity of about 10.5. Usually you would drink milk of magnesia to counteract, acidic problems with your stomach. Then ammonia, which is a common glass cleaner that we sometimes will use this in lab as well. It can be important as a base. Has a pH of about 11. And finally, bleach, as a common household reagent, has a basicity, or is basic, and has a pH of about 12.0. Finally, on the very high end, we have a solution of lye, which is 1 molar sodium hydroxide, which has the highest value that we commonly refer to with a pH of 14.0. Okay, so given that, looking at this pH scale, why don't you go ahead and label each of these solutions from your sample exercise sheet as acidic, basic, or neutral. Go ahead, give it a shot. Pause the video here, and then when you come back, we'll take a look at the answers. So go ahead, pause. Okay, let's go ahead and take a look here. So first up, we have HCl with a pH 1.5. Well, 1.5 is definitely less than 7, right? So that is, oops, there we go. So that's definitely going to be acidic. Okay, pancreatic fluid, and it tells you that the hydronium ion concentration is 1.1 times 10 to the negative 8th. Well, 1 times 10 to the negative 8th is actually less than 1 times 10 to the negative 7th. So that would suggest that this is basic. Sprite soft drink, trademark, there we go. The pH is 3, of course, that's acidic because it's less than 7. pH equals 7.0, that's exactly neutral. Okay, here's a good one. The hydroxide ion concentration equals 3 times 10 to the negative 10th molar. Well, that's less than 1 times 10 to the negative 7th. So that means you have a low hydroxide ion concentration, which means you have high hydronium ion concentration, and so you have an acid. And then finally, the hydronium ion concentration is 5 times 10 to the negative 12th. Well, that's less than 1 times 10 to the negative 7th. So this must be basic. Okay, let's see how we did. Yeah, looks pretty good. Acidic, basic, neutral, acidic, basic. Yeah. Okay. Now, how do we calculate the pH? Well, it turns out that this is a little easier than you might think. The P here is like an old function that people used to use a long time ago in the mathematics. And all it is it just means the negative log. So pH just means the negative log of the concentration of H, or the hydrogen ion, which we know is better modeled as the hydronium ion, right? If you have a hydrogen ion in water, I'll just kind of like draw it out here. I don't think I got to draw it out last time because my pen tablet wasn't working. What happens actually is the lone pair on this oxygen is actually going to form a covalent bond with this hydrogen ion. And that gives us the hydronium ion altogether like that. So this is what the hydronium ion actually looks like. And again, in water, this proton is so reactive that it is going to form this bond definitively over being alone in solution. So that's why we talk about the hydronium ion a lot. Now, all you have to do basically is, depending on your calculator, how you're going to enter this in. For this calculator, what I have is I have the sequential entry calculator. So the way I'm going to have to enter this is I first have to enter the concentration of the hydronium ion, which in this case 1.0 times 10 to the negative 2. So I go 1 EE 2 negative. Okay, 1 times 10 to the negative 2. Apologies, I know that's flipped. Okay, and then and now I'm going to press the log button. Log. So for me, my log button is right here. Okay, and then it's the negative log, so I have to press the negative button, which is all the way down here. So I have to press, basically for me, for this type of calculator, I type in the concentration, then press log, then press negative. Now, if you have like a line entry calculator, you'll just enter this whole thing in as it is. So it's the negative sign, the log button, and then the concentration. But that'll be dependent on your calculator. If you have any questions with your calculator, just let me know and I'll take a look. Okay. Oh yeah, so this, okay, no. Here's what I wanted to say. So here is the deal with significant figures. It turns out significant figures are really annoying when it comes to logarithms. It's even more complicated than what we talked about so far. And the way it works is the number of significant figures in your response here is going to give you the number of decimals in the pH value. So if we have two significant figures for our hydronium ion concentration, that means we know our pH to two decimal places. So that's why even though we got 2, we need to report it as 2.00 because we had two significant figures for our hydronium ion value. Now the tenths, the ones digit here actually comes from the what was I trying to say? The power of 10 that's available here for the molarity. So that basically doesn't count as a significant figure. Again, the reason that this gets so confusing is because using a logarithm value, basically the placeholders become significant in the logarithm value, even though we know the placeholders in a measurement don't count. That's why it gets so confusing. But the way that you can remember it is, again, count the number of significant figures in your hydronium ion concentration. That'll give you the number of decimal places you need for your pH value. Okay, now, how does this factor in to the pH scale? So the pH is a logarithm scale, right? We literally just said, okay, the pH is calculated based as a logarithm. So this is a classic example of what's called a log scale. When you change one pH unit, that means that there's been a 10-fold change in the hydronium ion concentration. So pH 2 means that you have 1.0 times 10 to the negative 2 molar hydronium ion concentration. If you have a pH of 3.00, well, you've gotten less acidic, right? And the way that you've gotten less acidic is you have a lower hydronium ion concentration. For 3.00 pH, the hydronium ion concentration is 1.0 times 10 to the negative 3rd molar. And it goes down from there. At pH 4.00, the hydronium ion concentration would be 1.0 times 10 to the negative 4th. Okay, let's do an example here. Aspirin, which is acetyl salicylic acid, was the first non-steroidal anti-inflammatory drug, also known as NSAID or NSAID, or NSAID, I think they say sometimes, used to alleviate pain and fever. If a solution of aspirin has a hydronium ion concentration of 1.7 times 10 to the negative 3rd, what is the pH of the solution? Now, if you feel pretty comfortable, you should go ahead and try this one now. Of course, we'll have a sample exercise in a few moments, but until then, just give this a try. Okay, so if we know the hydronium ion concentration, then to calculate the pH is a relatively simple example, or relatively simple calculation. We know that the pH is the negative log of the hydronium ion concentration. So we just need to take the negative log of, in this case, 1.7 times 10 to the negative 3rd. So again, the way I do that on my calculator, because I have just a simple standard scientific calculator, I'm going to enter 1.7 and use the exponential button, which in my case is EE. And it has to go to the third power, sorry, the negative 3rd power. So 1.7 times 10 to the negative 3rd. Hopefully you're pretty good at that by now. Again, if you have trouble with that, just let me know. Okay, so that's how we enter this number. Then we're going to press log, like this, okay? And then, yeah, of course, sure enough. Oh, and then, sorry, you press the log and then the negative button, and then your calculator display should read 2.769551079. Okay, so that's our calculator display. Now we have to apply our significant figures rules. So because we have two significant figures in our concentration, we're going to have two decimal places here. So we have to round to the hundredths place, which I think should be 2.77 when we're all said and done. And sure enough, 2.77. Yeah, okay. So that's how we're going to calculate pH. Now, why don't you go ahead and give it a try? What is the pH of a solution that has a hydronium ion concentration of 4.0 times 10 to the negative 15? pause the video here, give it a try, and then when you come back, we'll take a look at the answer. Go ahead, pause. Okay, we're back. So pH equals 4.0, or sorry, the hydronium ion concentration is 4.0 times 10 to the negative 15. So the pH is just going to be the negative log of that value. So we enter in our calculator 4.0 times 10 to the negative fifth. Okay, press the log button and the negative button. Oh, whoops, sorry, this is fifth and negative fifth. That's a little confusing. Apologies here. Let's go ahead and do the one that we said here, 15th, and then we'll do the fifth. Because I made a mistake here with this, the top part here. So I said initially 4.0 times 10 to the negative 15th, negative log. So for this one up here, the pH would be, you read it as 14.3979. To 2 decimal places comes out to 14.40 would be the correct answer. Now for the book here, it actually meant 4.0 times 10 to the negative fifth. So if it's 4 times 10 to the negative fifth, take the log and take the negative of that, you end up with 4.39794,000. Okay, so the correct number of significant figures, we have 2 significant figures. That means we have 2 decimal places over here. So 2 decimal places comes to 4.40. Apologies for that. I made a mistake on this one here. Okay, now, not only can we calculate the pH if we know the hydronium ion concentration, the reverse is true as well. We can calculate the hydronium ion concentration from the pH. And the way that we do that is by using something called the anti-log. Okay, and usually your anti-log, it's not, unfortunately, it doesn't show up as the anti-log on here. It usually just looks like the 10 to the X button. For me, when I press Shift or the second button, right above my log key, there's a 10 to the X button there. So when I want to take the anti-log, I'm just going to press second log like that. And the way that I have to do this, so it's going to be 10 to the negative pH value. So the way you're going to enter this in here is, here, I guess I don't know why I didn't have an example here, but if you have a pH of 3.0, to take the, to find the hydronium ion concentration from that, what you need to do is take your pH value, enter in the negative on your calculator. So note, I have negative 3.0 here. Then press the second and log key, and that'll give you your answer. In this case, it's 0.01. And the significant figures are just in reverse. So here we have 1 decimal place. That means we have 1 significant figure here. So it should be 0.001 molar. Right, okay. So the next thing that you need to do is, oh, I guess, yeah, so you could just do it this way. That's easy enough, right? Now, in this case, though, this is what I was talking about. So you take 3.42 and make it negative. So it's negative 3.42. Then press your anti-log or 10 to the X button and make sure it shows up in scientific notation. What you end up doing is you get, so in this case, it's 3.801 times 10 to the negative fourth. And when you round to the correct number of significant figures, the pH value has 2 decimal places. That means we have 2 significant figures for our hydronium ion concentration. You end up at 3.8 times 10 to the negative fourth, to the correct number of significant figures. Okay, so all this means is basically that the hydronium ion concentration, the pH, and the hydroxide ion concentration are all interrelated, right? We saw that the hydronium ion concentration times the hydroxide ion concentration always has to equal 1 times 10 to the negative 14th. Also, we see that the pH is directly related to the hydronium ion concentration, or I should say inversely related to the hydronium ion concentration, logarithmically related. Okay, so that is pH and how you can calculate the hydronium ion concentration. I'll just say right now, I'm not going to put this anti-log on here. I am just going to give you calculations of pH on the exam rather than calculations of the hydronium ion concentration. Okay, now, of course, what we're trying to do in this class is set you up for an understanding of how chemistry works in the body so that you're set up in the future to understand how these things interact with human bodies. And of course, acids and bases are a really important part of the body. So that's what we're going to look at in section 10.7. Well, first we're going to talk about the reactions that they have, and then the different types of cells that can use this. Your gastric acid, for example, contains hydrochloric acid, and that's produced by cells, what are called parietal cells, that are in the stomach. And basically, when you put stuff into your stomach, so when you eat food, HCl is going to be secreted by these parietal cells until you have a low enough pH for the digestion to take place. And pH reaches about 2. I think we said 1.6 previously. Okay, but first let's go ahead and talk about some of these reactions in general before we get into the specifics of it. So we've seen in lab that acids will react with certain metals to bubble and produce hydrogen gas. For example, we put zinc in HCl, I believe it was, and we saw bubbles form. We know that acids react with bases and they produce a salt and water. We saw that in lab. And then finally, acids will react with bicarbonate and carbonate ions to produce carbon dioxide gas. So when we say the word salt, it's important to note here, just like we mentioned in lab, the salt is an ionic compound. And this ionic compound, crucially, cannot have either hydrogen as its cation or hydroxide as the anion. It just has to be some ionic compound. It's kind of a generic word for an ionic compound. Okay, so the types of reactions that can occur. When you put a metal such as potassium or zinc in hydrochloric acid, the potassium replaces the hydrogen and you get a single displacement reaction where you form a new salt, in this case potassium chloride, and hydrogen gas. The same thing happens with zinc when it reacts with hydrochloric acid. It produces zinc chloride and hydrogen gas. And the metals that it will react with include potassium, sodium, calcium, magnesium, aluminum, zinc, iron, and tin. You don't need to memorize that. It's just an example that only some metals are reactive enough to react with the acid. Other metals will not react with acid. Okay, so let's go ahead and give it a shot. Given this setup here, can you write a balanced equation for the reaction of magnesium metal with hydrochloric acid or the reaction of aluminum metal with nitric acid? Let's go ahead and do the second one first, and then we'll take a look at how we answer the first one. So if you're feeling confident, go ahead and pause the video. If not, I'm going to walk you through it at this point, and we will take a look here. So if we have aluminum metal, and we're reacting it with nitric acid, well, we can recognize that we have a element and we have a compound. So if there's a reaction that's going to take place, it would be a single displacement reaction where the element aluminum displaces the hydrogen to form a new compound, aluminum nitrate. Okay, so now the first thing that we note is if hydrogen is displaced, then it's displaced as its element form, hydrogen gas. Okay, and then that means that the resulting compound has to be whatever anion is left over, nitrate, and then the cation, aluminum. So nitrate, we know that's NO3 minus. How about aluminum? What's the charge on the aluminum cation? Hopefully you remember it's 3 plus. So when we put this all together, it should be AlNO3, NO3, sorry, I messed that up. There's 3 nitrates to balance the 3 plus charge from the aluminum cation. Of course, that's not all. We have to balance the equation now. And this is a tricky one here. because the first thing that we want to do is we notice we have 3 nitrates here, and we only have 1 nitrate over here. So we would need to put 3 of these. But unfortunately, that doesn't balance our hydrogen here because we need 2 of them. So what we can do is we can say that this would be balanced if we had 3 halves of a hydrogen molecule and 1 of aluminum, 3 of nitric acid, 3 halves of this, and then 1 of aluminum nitrate. Now, we can't keep everything like that because it's not right to have a balanced equation with a fraction coefficient. What if we just distribute a 2 throughout the whole thing? We get 2 times aluminum. Then we get 2 times 3, that's 6 nitric acid. Reacting to form 2 times 3 halves, 3 hydrogen gas, and 2 aluminum nitrates. And now we have our balanced chemical equation. Okay, so so note here the salt in this case is the aluminum nitrate. Okay, sorry, I guess I should take a second, pause the video here, try to come up with the reaction for magnesium metal and HCl now, and now we'll look at the answer when you come back. So pause it here, and let's take a look at the answer. So if magnesium metal reacts with hydrochloric acid, you're going to form magnesium chloride as the salt, MgCl2, and H2 as the H2 gas. Yeah, something to note, this one was a lot easier to balance than this one here. Okay, now the next thing that can happen is acids will react with carbonates and hydrogen carbonates to produce carbon dioxide gas, whatever salt is left over, and water. So for example, if you take hydrochloric acid and react it with calcium carbonate, you have what's called a double displacement reaction, where the cation of the first picks up the anion of the second to form carbonic acid. That would be H2CO3. Okay, and then the cation of the second picks up the anion of the first, that's calcium chloride, which is what we see right here. Now the thing is, carbonic acid decomposes. So this actually goes away and leaves us with water and CO2 as a gas. So this is a tricky one to recognize, but once you recognize once you see the carbonic acid, you know that that's going to decompose into water and carbon dioxide. Okay, so let's go ahead and do a different example here. So again, this is like the double displacement reactions from the previous chapter. Let's go ahead and do B together first. And then we'll do A. I'll let you have a moment to do A. But I want to do B because it involves hydrogen carbonate. So these are 2 ionic compounds, an acid and an ionic compound. And when they get together, you have to check and see, are they going to decompose or are they going to form a precipitate? So what we do is we take the cation of the first, that's the hydrogen ion, and combine it with the anion of the second, that's hydrogen carbonate, HCO3 minus. When they come together, that forms H2CO3. Okay. Now the thing is, H2CO3 immediately is going to decompose. And so that's actually going to be water as a liquid and carbon dioxide as a gas. And then we have the cation of the second, sodium, and the anion of the first, chloride. When they come together, that's just a simple sodium chloride. So that's our simple salt in that case. Okay, and so here we don't actually have to balance any of this because it's all 1-to-1. So you don't need to balance anything beyond that. One thing I want to point out is if you do have to balance this at any point, sometimes it's easier to balance it when you have it as H2CO3 before it decomposes into H2O and CO2. Sometimes that's easier to do. Anyways, go ahead, give A a shot here. Oh, oops. Give A a shot, and then we'll take a look at the answer on the next slide. So pause the video. Okay, let's go ahead and give it a shot. With A, magnesium carbonate, and hydrobromic acid. the hydrogen from hydrobromic acid is going to pick up the carbonate from magnesium carbonate, and that's going to form, again, H2CO3. So it's H plus and CO3 2 minus. That comes together as H2CO3. Note that you need 2 of these. That's going to be important for balancing the equation later on. Then we have magnesium as the first cation, and bromide as the second anion. Those come together, they form magnesium bromide, MgBr2. That's our salt. Okay, now H2CO3 is going to decompose into CO2 and H2O. So our final equation would be magnesium carbonate reacting with 1 mole of magnesium carbonate reacts with 2 moles of hydrobromic acid to produce 1 mole of magnesium bromide, 1 mole of carbon dioxide, and 1 mole of water. Okay, and finally, the actually important type of reaction is the neutralization reaction. And this is basically what happens when an acid mixes with a base. And in this neutralization reaction, the same sort of theoretical reaction as what we've seen with any double displacement reaction, where the cation of the first, in this case the hydrogen ion from the acid, reacts with the anion of the second, in this case the hydroxide ion of the second, and the cation of the second, sodium, forms a compound with the anion of the first, chloride. So your salt is just sodium chloride, like what we've seen. But there's a special reaction that occurs when a hydrogen ion meets a hydroxide ion. They come together and they form water. So this H2O, you can think of it almost as like HOH, right? So H plus and OH minus would form HOH. But of course, HOH is just our good friend, water. So the way this always works is that, or one way that you can do this basically is if you notice that the strong acid and the strong base, if you have a strong acid and a strong base, that means you have fully dissociated hydrogen ions and chloride ions in solution, along with sodium ions and hydroxide ions. That means that when you form, when this hydrogen ion meets this hydroxide ion, it's going to form a water molecule. Now, the chloride ion and the sodium ion are just aqueous on both sides of the equation. They're what we call spectator ions. And so they don't really participate in the reaction. So the net ionic equation for any of these, that just means what is actually happening. It's 1 mole of hydrogen ions reacting with 1 mole of hydroxide ions to form 1 mole of water. Okay, so now if you're going to balance the neutralization reaction, one of the easy ways to do it is that you just want to balance the hydrogen from the acid with the hydroxide ion from the base. So if you recognize that you're balancing a reaction that's a neutralization reaction, well, note here, this nitric acid has 1 proton, right? It's 1 H plus and 1 NO3 minus. But magnesium hydroxide has 2 hydroxide ions. So to balance that, you need to put a 2 here to make sure that you have enough hydrogen ions to react with the right number of hydroxide ions. And then finally, make sure that your salt, in this case, matches what you know, which is you have the magnesium ion and you have the nitrate ion. So of course, to balance the charges, it's got to be MgNO3 2. Cool. All right, so let's go ahead and give it a shot. Why don't you try to balance these equations and come up with the correct coefficients? I've listed 3 possibilities here. So why don't you go ahead and pause the video now, and when I come back, we'll take a look at the correct answers for both of these. So go ahead, give it a shot, and once again, we'll be back in just a moment. So pause the video, and let's take a look. Okay, so for HCl and, hold on. For HCl and AlOH3, note we have 3 hydroxide ions. So that means that we're going to need 3 HCls. If we have 3 HCls plus 3 hydroxides, that means we're going to form 3 waters. That gives us 3 chlorides and 1 aluminum, which balances out here. So I get 3, 1, 1, 3, or C. Ooh, this is a good one. So we have 2 hydroxides, we have 3 hydrogen ions for the reaction of barium hydroxide and phosphoric acid. So in this case, I would actually lean on our previous balancing problems where, look, we have 3 barium ions in the products. To get those 3 in the reactants, we have to put 3 in front of the barium. Likewise, we have 2 phosphates in barium phosphate. So to get that, we have to put 2 in front of it here. To balance it all out, that gives us 3 times 2, 6 hydroxides, 2 times 3, 6 hydrogens. That's going to form 6 waters. So I got 3, 2, 1, 6, which would be B. So again, you can be a little clever when it comes to balancing these equations here. Okay. Finally, titration. Now, this is what we did in class, in lab, so we're not going to spend too much time on it in lecture here. Again, note that titration is a laboratory procedure, and it's really useful determining the molarity of an acid, or you could potentially determine the concentration of a base as well. Note here that if you have an acid solution of unknown concentration, then you can add a base solution of known concentration. And based on when this hits the endpoint, in other words, when all of the acid is used up, then you can determine the moles of acid that were in the solution and then the molarity of the acid as long as you measured a good volume. Okay, so the indicator phenolphthalein, it turns pink at the endpoint, and that is just a way that you know that all of your acid's been used up. So even in a very slightly basic solution, phenolphthalein turns pink. So yeah, at the endpoint of a titration, this is when the moles of the base that have been added are equal to the moles of the acid that you started with in solution. So if the concentration of the base is known, you can use the volume of the base that you added with this equipment, the burette, to reach that endpoint, and you're then able to measure the concentration of the, first off, the number of moles of base that you added, and from there, the number of moles of acid that were in here to react with it. Okay, so here's an example of a calculation, again, that we did in lab. What is the molarity of an HCl solution if 18.5 milliliters of 0.225 molar sodium hydroxide is required to neutralize 0.0100 liters of HCl? So start always with your balanced equation. Now for HCl and NaOH, that's easy enough. It's a 1-to-1 ratio, reacting to form 1 mole of sodium chloride, 1 mole of water. So start with the balanced equation and note we have the correct number, or we have a recorded number of milliliters of the sodium hydroxide, and we know the concentration of the sodium hydroxide. So from here, we can determine the number of moles of sodium hydroxide. If we know the number of moles of sodium hydroxide, then we can use the mole-mole factor from our balanced chemical equation to determine the moles of HCl. Once we do that, if we divide it by liters, then we can determine the molarity of the HCl solution. So the math is pretty straightforward. You take your 18.5 milliliters of sodium hydroxide, convert that into liters so that you can use your molarity. The molarity being 0.225 molar means that it's 0.225 moles of sodium hydroxide for every 1 liter of sodium hydroxide solution. So now we're in terms of moles of sodium hydroxide. We know that we use 1 mole of HCl for every 1 mole of NaOH from our balanced chemical equation here. That gives us 0.00416 moles of HCl. We know that's what was in the flask when we did the reaction. If we divide that by our volume in liters, 0.0100 liters of HCl, then we get our concentration of 0.416 molar HCl. Okay, so why don't we go ahead and give this a try? Again, this should be very similar to math that we did in lab, just using different volumes and different concentrations. So what is the molarity of an HCl solution if 25.5 milliliters of 0.438 molar sodium hydroxide is required to neutralize 0.0250 liters of HCl? Pause the video, and when you come back, we'll have take a look at the answer. So go ahead, pause. Okay, so once again, we're given the volume of a known molarity sodium hydroxide, and then we're given the volume of HCl that was neutralized. So start as always with our balanced chemical equation. Again, very straightforward. HCl plus NaOH reacts to form NaCl and water. Now, what we're going to need to do is we need to determine the number of moles of HCl. So in order to do that, we need first the number of moles of sodium hydroxide. If we take the milliliters of our sodium hydroxide solution, convert it to liters, then we can use the molarity to determine the number of moles of sodium hydroxide. From there, we know it's 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide, and that gives us the moles of HCl. Finally, we divide by the liters of the solution, 0.0250 liters of HCl. That will give us the molarity. Okay, so put it all together. It's 25.5 milliliters times 1 liter divided by 1,000 milliliters for our NaOH solution. Then we use the molarity. 0.438 molar means that there's 0.438 moles of sodium hydroxide per 1 liter of solution. And then finally, the mole-mole factor. We know that there's 1 mole of HCl for every 1 mole of sodium hydroxide. That gives us here our number of moles of HCl, 0.0112 moles HCl. Divide that by the liters, 0.0250 liters of HCl. And that gives us our answer here, 0.447 molar HCl solution. Okay, so last note here, antacids, basically, this is just how things work in your health. So we mentioned before that, if you drink acidic substances, it can lead to heartburn. If you have excess stomach acid, basically, if your stomach acid pH either gets too low or it is able to leak out into your esophagus, you may experience heartburn symptoms. So antacids like Tums, for example, I don't know if I'm supposed to, I don't get paid by the Tums Corporation or anything, but are made up of mixtures of like aluminum hydroxide, magnesium hydroxide, calcium hydroxide. And the reason that we use these in particular is that they're not soluble in water. So whatever levels of hydroxide ion you do have are going to react in your stomach, but not go into the intestinal tract. And yeah, here's a list of them here. So, here we go. Tums is calcium carbonate, actually. Okay. So Tums is calcium carbonate. The stronger ones are going to be your hydroxide-based ones. So, but calcium carbonate's nice because it's chalk. It's not going to hurt you, and it's not going to be damaging either. It'll just make you burp a little bit because you produce carbon dioxide. Alka-Seltzer is really nice too. I don't know. That's an old one, but I remember when I used to get really bad headaches on Sunday mornings, I would take an Alka-Seltzer and I'd feel better. Oh yeah, the final section here. Sorry, I almost forgot. There's one final section, which is about buffers. And we're just going to kind of define buffers here. We're not going to talk in too much depth on them. But basically, the idea of a buffer is that if you have a system where you have an acid that's present to neutralize hydroxide that's added, and you have a base that's present to neutralize acid that's added, then you have a system that keeps your pH within a very narrow range. And the reason this is important is because our biological proteins operate within a very narrow range of pHs, whether they're in the blood, the stomach, the bile, the lungs, in the interior of the cell. It's important that the pH doesn't change very significantly, very quickly, because we need to make sure that these proteins and enzymes are operating efficiently. So for example, if you have just a neutral glass of water and you add in 1 times 10 to the negative third molar acid, well, your pH is going to change by 10 to the third. Or I should say the pH changes by 3 because the concentration of hydronium ion changes by 10 to the third. Similarly, if you add in the similar concentration of hydroxide ion, the pH changes up by about the same amount. That's a real problem, again, in a biological system. So buffers are able to resist that change by having internally an acid component that reacts with the bases that's added and a base component that reacts with the acid. For example, in your blood is a very complicated system of carbonate, hydrogen carbonate, and some level of carbon dioxide. So the way that this works is, again, you just have an acid component that will react or absorb the hydroxide ions, and you have a base component that reacts or absorbs the hydronium ions. For your blood, again, that's a very narrow range, close to 7.4 pH. If you affect the pH of the blood, then you're not able to uptake oxygen efficiently, and it's going to affect your cells as well. So you can imagine that would be a real problem. Okay, so the way a buffer solution is actually formed is that a buffer solution has to contain a combination of acid-base conjugate pairs. In other words, the acid component has to be a weak acid, and then the base component has to be the conjugate base of that acid. So this is acetic acid here. When acetic acid gives up its proton, it forms acetate. So if you have a mixture of acetic acid and acetate, then you have a buffer system that resists changes. Basically, any acid that's added will react with the acetate to form acetic acid. Any base that's added will react with the acetic acid to form acetate. So it kind of ping pongs back and forth as long as you don't destroy the capacity of the buffer. So the way that you can actually do this is if you take acetic acid and mix it with sodium acetate, then you have a concentration of acetic acid, you have a concentration of acetate, and it's almost like they're sharing protons back and forth. And so you're able to resist the change if you add hydroxide ion. In this case, the hydroxide ion decreases the concentration of acetic acid, but only forms acetate rather than having hydroxide ions in solution. So this barely affects the pH. We're not going to do the math or anything, but yeah. Now, what if you took acetic acid, or what if you took this buffer system and added acid? Well, the acid is going to react with the acetate ion to form more acetic acid. So in this way, it just kind of ping pong back and forth between these concentrations of acetic acid and acetate, and you don't actually affect the concentration of hydronium ion or hydroxide ion in the system. And so the pH does not change very much. Now, fortunately, we don't have to do this math in class. The math is a little complicated. If you go on to take Chem 1A and Chem 1B, you will do a lot of this math, but for today, we don't have to worry about that. Okay, so which of the following combinations make a buffer solution? Okay, so now I promised you that we would have some of this stuff not on the test. And so this, I'm just going to tell you, we're going to have one of these combinations from this slide on the test. I'm going to ask you basically, do they make a buffer solution or not? And it's not going to be tricky because we're going to go through it right now. So if you mix HCl and KCl, does that make a buffer solution? Well, HCl is a strong acid. Remember, a buffer has to be a weak acid and a salt of the conjugate base. So even though the conjugate base would be chloride, because HCl is a strong acid, it cannot be involved in a buffer. Now, if you take carbonic acid, H2CO3, and you mix it with sodium hydrogen carbonate, well, this is a mixture of H2CO3. And what do you get if it gives up a proton? Well, you would get hydrogen carbonate. In other words, you get the acid and its conjugate base. How about H3PO4 and NaCl? That makes no sense, right? Those aren't related in any way. But how about acetic acid and potassium acetate? Sure enough, acetic acid is the acid, acetate is the conjugate base. So this would be a buffer. So again, you can expect to see one question, just exactly like this on the test. So you are prepared now. Okay, so that wraps up our discussion. Again, I want to emphasize buffers are really important in biological systems, and this is how they work. You have to have a weak acid and the salt of its conjugate base. Okay, but that does it for chapter 10, which means now you should be ready for exam 2 if everything is going swimmingly, and I'll let you know if anything changes from there. But you should be ready for that. Of course, keep working on the homework. And of course, if you have any questions, make sure to comment in the comments down below. Until then, I will see you soon and have a nice day. Bye-bye.